What happens when your data in your test bench refuses to stay fixed? One packet is tiny and the next packet is massive. Sometimes you need extra memory, sometimes you don't. So how do you design a verification environment that adapts on the fly? SystemVerilog brings in a way to make arrays, queues, and associative arrays to grow, shrink, and adjust at runtime. No wasted space, no rigid limits, just flexibly that follows the data. For simulating protocols like Ethernet and USB, to injecting random errors, to scaling scoreboards and monitors, this capability quietly makes the test benches more realistic and resource-friendly. In this episode, we uncover how dynamic memory allocation transforms verification by making it adaptive, efficient, and future-ready. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the dynamic memory allocation benefits. Next, we'll talk about flexible test data handling. Next, we'll talk about the aspect of efficient resource utilization. Next, we'll talk about dynamic stimulus generation. Moving further, we will show the importance of protocol and packet simulation. Next, we will show the importance on dynamic error injection. All of this with respect to the dynamic memory allocation. Going further, we will talk about adaptive verification components. We will talk about functional coverage collection. We will talk about queue operation for transaction management. We will talk about associative array in lookups and concurrency testing. So all of the aspects will be covered with respect to the dynamic memory allocation that has been newly introduced in SystemVerilog as compared to the Verilog. So without any further delay, let's begin. Why dynamic memory allocation is introduced? In real-world verification, data sizes are rarely fixed. To handle unpredictable data, SystemVerilog introduced dynamic memory allocation. This allows arrays, queues, and associative arrays to adjust their size during the runtime. This capability gives verification engineers the flexibility to handle runtime variations efficiently, making test benches both adaptive and resource-friendly. So let us move on to the next slide without any further delay. Dynamic memory allocation benefits. Dynamic memory allocation provides flexibility, efficiency, and adaptability. Instead of wasting space with fixed arrays, memory is allocated only when needed and adjusted dynamically. These benefits directly translate to scalable verification, where test benches adapt to runtime conditions without hard coding the limits. Dynamic memory allocation allows the allocation of memory during runtime, enabling structures like dynamic arrays, queues, and associative arrays to grow, shrink, or adapt the varying size of data that may not be known during compilation. So we are talking about real-time verification scenarios. And real-time, you do not know how much data is getting in the TXRX zone. So you have to prepare for it. And the dynamic memory allocation is the key instrument to deal with that. And this instrument can be used in multiple ways, which we are going to explore in the upcoming slides. Dynamic memory allocation is particularly useful in test bench environments where the data sizes often depend on runtime condition or randomization. Now, when I am talking about test bench, that means I am not talking about the Verilog test bench for the DUT. Rather, we are talking about the test bench for the subsystem level or the full chip level verification. The dynamic memory allocation has the following benefits. Flexibility allows handling data of various sizes, and by this episode you know there are different types of data structures available in SystemVerilog, borrowing them from various programming language concepts. Efficiency. Memory is used only as needed. That means where we need, we expand the memory. Where we don't need, we use smaller memory. Hence, the wastage of memory is not there, as well as due to the shortage of memory, there is no error is coming. Dynamic behavior. suited for scenarios where the size or the structure of data changes over time. During the verification execution, there could be different set of data packets coming in the TXRX zone. So in that case, the size of the packet might change. So the dynamic memory allocation helps to deal with those scenarios which are very much realistic. We are done. These benefits directly translate to scalable verification where test benches adapt to runtime conditions without hard coding the limits. We are done now. So let's move on to the next slide. Flexible test data handling. This enables handling variable size or dynamic test data, especially for protocols or scenarios where the payload size are changing. Helps to simulate real-world scenarios very dynamically. Here goes our example code. We have module, then flexible test data, and it's a module name. Here we use dynamic array for variable data size, and this is the dynamic array. And here we start our initial block, and here we define a size variable with random variable, and we keep a range. That means between 5 and 15. Now it's time to allocate the memory. We use the data and use the new keyword, and we use size. So data is our point of concern. For each data, we have the index I and we begin, and we assign each data as a random number. So this assign random values, and at the end, the entire data is filled up, which we have defined here in this line. Next, we display the contents. For that, we use the display, which acts like a printf function, and there we print the data, and we end the initial block here, and then we end the module. This dynamically allocates an array of random size and assigns random values, mimicking the variable size test data verification. This ensures our verification reflects real-world cases, making the design more robust under dynamic traffic condition. So we are done with this particular slide. So let's move on to the next slide. Efficient resource utilization. One of the biggest advantages of dynamic memory allocation is resource efficiency. Memory is used only when needed and freed afterward. Allocates memory when needed, conserving the simulation resources, frees up the memory when no longer is in use, enabling large-scale simulation. This helps because we are doing the verification, right, in a physical computational resource. Even with the high resource, high memory, we have some limitation of misuse of memory that we stop here and we do the efficient utilization. Here goes our code. We give the name of the module as resource utilization, and then we define the dynamic array, and here is the array. We begin the initial block here and we allocate the memory data new, and then we give 10. Now for each of the member of the data, we use a for each loop and we assign it for data equal to I, okay, and this way we assign the value and free the memory afterwards. How we do that? We use a predefined method. As you know, the SystemVerilog is a object-oriented language, and we have a delete method inbuilt. So we use the data.delete to delete the entire data and free up the memory. Then we check it. If data.size is 0, that means here we also have another predefined method for the object, that is size, give the size. If it is 0, we print that memory has been freed, and we end the initial block and end the module here. Thus, allocates memory when needed and deletes it afterward, conserving the simulation resources. That means unnecessarily we have a fixed RAM, so we are not blocking parts of it for the entire simulation time. We block it as much as we need and then we free it up. This allows larger simulations, that means the full chip or the test chip level simulation, to run smoothly by conserving resources and avoiding unnecessary memory usage. We are done with this particular slide, so let's move on. Dynamic stimulus generation. Dynamic allocation enables us to generate randomized test stimuli at runtime. This is crucial for exporting constrained and edge case scenarios. So, this is used in generating randomized test cases where the data structures, which are borrowed from different programming languages, as we have learned in the previous slides, needed to adjust based on runtime condition. That means how long it is needed, after what time we don't need it. Supports creation of randomized, constrained, and edge cases test scenarios with dynamic data. Because in a test bench, right, we have to test multiple conditions, and all the conditions we cannot hard code. So we have to be in the random method to generate them. So we need a control over the memory, the physical memory that is getting allocated, so that the memory is not blocked and it can be used later on, and thus the efficient use for the stimulus generation. Here goes our example. we have module and it is called dynamic stimulus, and queue for dynamic transaction. So here we define the queue int and then we define the queue with $ here, and we start our initial block and we run a for loop here, and we use the method like push, right? Push back in the queue, and we give a random number here. That means we are using it as a queue, and we end the for loop here, and here we do the printing, that means the display, and here generated transaction, and we give the queue, and we end the initial module and we end the module with end module. Generates test stimuli dynamically using a queue reflecting runtime conditions. So this way we generate randomized and constrained edge cases. With this flexibility, verification environments can create diverse test cases, ensuring thorough coverage of possible behaviors. So we are done with this particular slide. Let's move on. Protocol and packet simulation. Communication protocols like Ethernet, IP, or USB involve packets of varying load sizes, that is different payload sizes. Dynamic memory allocation makes it possible to model these packets accurately. Thus, it is useful for modeling complex communication protocols where the packet sizes and structures may vary dynamically. As you know, we have borrowed a lot of data structure from other programming languages. Example are Ethernet frames, IP packets, that means TCP IP packets, USB data stream, there could be UART, PCI, different protocols. Here goes our example. We have the module, name it protocol simulation, and here we define a structure. We use type def for that, which you are already familiar with in case you have watched the previous episodes. Then we use struct keyword, and here we include address, source address, destination address, and payload. And this is, remember, dynamic payload. And we define a name for it, that is packet underscore T. And here we instantiate a object of it, the packet underscore T is PKT, that is packet. Next, as the initial block starts, what we do, we give the packet dot source address is 1 and destination address is 2. As this is object-oriented language, the dot separator you know already, and we are making use of that. Next, we have the payload. So packet dot payload is new, and then we have random number generation here using urandom, that is unsigned random number. And we give a range here. So we generate this way random payload size. Now we run a for each loop for each payload and we assign it with a random number. So here it is getting as random values. Then to print all the things that we have done, we use the display. Then we give the printf like structure here, as you know from C. And then we get the output here. And here we end the initial block and we end the module here. This simulates a protocol packet with variable payload sizes. This is a typical example for different frames like Ethernet, IP, PCI, USB. This could be different. The structure of this dynamic payload, right? This one, or the dynamic structure, not the payload only, could be different. But however, the philosophy and the theme remains the same. This way, we can simulate real protocol behavior, verifying that designs can handle unpredictable packet structures. We are done with this slide, so let's move on to the next slide. Dynamic error injection. Fault tolerance is a key part of the verification. With dynamic allocation, we can inject errors into data at runtime to test error handling mechanisms. Thus, it facilitates runtime insertion of errors into dynamically allocated data for test fault tolerance. Example, corrupt specific bits in a dynamically generated frame. This is a realistic scenario because when TXRX things are exchanging, right, in between each other, the data packets, there could be fault in some of the packet because of any reason. We can simulate that using this. So let us see the example. Here we define the module error injection, and here we have the queue for the data. We define the queue for the data as this, and then we start our initial block. We use a for loop, that is a conventional for loop, for pushing back the data for each of the indexes. Now we tend to inject an error into the random position. We have the error index here and we have the random variable to generate it, and here we use the range here from 0 to data size -1. Here the data, then error index, then -1. This is the error. We inject it, and then once everything is done, we use the print like statement, that is display, and here we print the entire data. We end the initial loop here and we end the module here. This injects error dynamically into the test data to validate error handling mechanisms. This provides a realistic way to validate how systems respond to corrupted or faulty data. We are done here with this particular slide, so let's move on. Adaptive verification components. Components like scoreboards and monitors often deal with dynamic data. Associative and dynamic arrays allows them to adapt to the changes during execution. Thus, it helps verification components like scoreboards, monitors, and coverage collectors can adapt to runtime data changes. Associative arrays and dynamic arrays are often used for managing runtime data storage and lookup. Let us see some example. Here goes our example. We have the module and name it adaptive scoreboard. So first we define a scoreboard using int, and here we have a string associative array for transaction tracking. Here we start our initial block and we have log transactions. We have scoreboard, then write as key and the value is 10. We have scoreboard, read as the key and value as 15. So this is basically like a hash table. And then we have to display the scoreboard. So what do? We do a run of for each loop on each of the key of the scoreboard, hash or hash table. And then we use a print statement, that is $display. And here we use the printf like syntax to print all the things. We end here the for each, then we end the initial block and we end the module. Adaptive scoreboard adjusts dynamically as transactions are logged. This adaptability ensures verification environments remain reusable and effective across different test conditions. Once you enter the SystemVerilog verification, you will understand the importance of each and every slide that we are talking in this discussion. We are done here, so let's move on to the next slide. Functional coverage collection. Coverage models also benefit from dynamic memory. By storing variable length transaction, we can collect coverage data that reflects real-time conditions. Thus, it helps supporting runtime collection and storage of functional coverage data. Example, store and analyze variable length transaction in a coverage model. Now let us see some examples. Here is our example. We name the module as functional coverage. We have int then cover data, and here we are dynamically defining it. We have initial then begin. Now we have cover data and allocate memory for the coverage data. So we are dynamically allocating the memory. Then for each covered data, that is indexed items, we use a random number generation method to feed the value. And now process and log coverage. We write the for each loop, iterating over entire set of data, and we use printf style commands here. So the entire data which we have constructed getting printed here. We end the for each. I think the for each is one line, so this end is for the initial, and we have the module ending with end module. Thus, it collects and processes dynamic functional coverage data. This is a typical short and sweet example. This leads to more accurate coverage matrices, ensuring that no significant scenario is overlooked. Again, I am emphasizing when you are doing the real-time verification, you will understand the importance of what we are touch basing in this discussion. We are done with this particular slide, so let's move on to the next slide. Testbench Scalability. Dynamic memory allocation promotes scalability by making test benches modular. Instead of fixing sizes, arrays, and queues can expand it with system complexity. So thus, it helps in making test benches more modular and scalable, as dynamic arrays and queues can adjust to the system complexity without hard coding the sizes. So this is the word, hard coding. We do not hard code. We make it flexible. Thus promotes use of verification environments across different configurations of a design. So we have variants of a design, then we can vary dynamically. Let us see some example. Here the module name is scalable test bench, and here we have dynamic array for test scenarios. Then we have string and we have the test scenarios. We have the initial begin here. Then we allocate the memory dynamically. Here the test scenarios with new and 5. So for the index 0 we define it scenario 1, and for index 1 we have scenario 2, as this is of string type. Next we use the for each loop to iterate over the test scenarios and print all the data it has within it. And here we end the initial block and end the module here. Dynamic arrays make the test bench scalable for various configurations. So this is how we are making the test bench scalable for different scenario, different requirements. And not to mention that all the cases that we have discussed throughout the discussion of today, we can have permutation of combination of multiple things. It's not fixed that the example we are giving and the examples we have given before, there could be permutation and combination as per the need of the verification. This makes the verification environment reusable across multiple design configuration without rewriting the code. We are done here with this particular slide, so let's move on to the next slide. Queue operations for transaction management. Queues are natural fit for managing transactions dynamically. They allow push and pop operations that mimic real transaction flows. Thus, it makes test benches more modular and scalable, as dynamic arrays and queues can adjust the system complexity without hard coding sizes. Again, we are saying the hard coding sizes. We are not hard coding, making it flexible. That is the beauty of dynamic memory allocation. It promotes reuse of verification environments across different reconfiguration or configurations of a design. So let us see some examples. Here goes our example. We have named the module as queue operations, queue for transaction, and we define the queue as this. And we start the initial block and we use pushback method. Again, I am emphasizing that SystemVerilog is an object-oriented language. So many default methods are there for queues. One of them is pushback to push the data into the queue. And here a 10, and then we push back 20. And this is done. So we will do a while loop here to pop and process the transactions. We run the while loop on the transaction size greater than 0, and here we begin. And we print using the display that processing transaction, this is %d, and here we pop out. So this is another predefined method, as SystemVerilog is an object-oriented language. Pop front. So queue, for this queue we are pushing it from back and popping it from front. Okay, so the first which has been pushed from back will come at first. Okay, so here we end the while, and then we end the initial, and then we end the module here. Queues allows efficient management of transaction with dynamic push and pop operations. This results in efficient transaction management, ensuring test benches handle dynamic workloads smoothly. We're done with this slide, so let's move on to the next slide. Associative array in lookups. Associative array make runtime lookups very easy. By mapping keys to values, they simplify tasks like tracking transaction states. Thus, it allows efficient implementation of lookup tables, mappings, or key value pair searches in a test bench. Example, mapping transaction IDs to their respective states in a tracker. Now let us see some example. Here goes our example, and here it is named, the module we have named associative array lookup. So we define the associative array like that. Here we have memory map, and then we have string here. We have the initial begin here, and then as a key we are writing address 1 giving value 100, address 2 we are giving value 200, and then lookup and display. So now we will print using the display command, and here at memory IDDR1, that is address 1, we have the value which is using the lookup. That means here we are getting the value which we have stored here, and we end the initial and we end the module here. This is a very simplistic example. In real time, this could be dynamically created and dynamically accessed. Associative arrays enable dynamic key-based lookups for runtime mappings. This makes test benches more powerful, enabling flexible and fast key-based data retrieval. This is very important because if we have a lookup table, we can retrieve some of the data based on the names of the keys, because this is key value pair of a lookup table or a hash table, as you know from programming languages. So we are done with this particular slide. So let's move on to the next slide. Concurrency testing. Dynamic memory allocation also supports concurrency testing. Mechanisms like mailboxes allow safe communication between parallel processes. Thus, it facilitates the modeling and verification of concurrent operations with dynamic memory, that is mailboxes and semaphores. These concepts you will later become familiar when we go for the SystemVerilog for verification paradigm. It is used to test the synchronization mechanisms between multiple components. Now let us see some example. Here goes our example. We name the module concurrency test. We define a mailbox. This is mbox, and here we start the initial block, and here we instantiate an object that is with new, and we do the fork and join process here. The first fork here we have the mbox, then put 10. So put, again we say that the SystemVerilog is a object-oriented language, and hence we have many predefined methods associated with the different entities here. So put is one of the method, and in the next fork what we have, we use a print statement received %0d mbox.get. So here we are using the method put, and here we are using the method get. And since this is our old style fork join, so it has to be in proper sequence. So put is done, then get is done. And here we end our initial block and we end the module. So concurrency is managed dynamically using mailbox for inter-process communication. That means for the inter-verification paradigm, we have two processes and they are doing exchange. So there what we have, the concurrency testing and inter-process communication. You will know about all these paradigms when we go for the detail in SystemVerilog for verification paradigm. There we will come across all the concept in terms of code and as well as philosophy. So for now, you just learn this. This helps verify synchronization and ensures designs behave correctly under current operations. We are done with this particular slide, so let's move on. And we come to the end of our today's discussion. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislike, put that as in words in the comment section down below. And bye for today.